Hello there, stargazers, and welcome to The Sleepy Astronaut, where the universe shares its secrets and science becomes a gentle journey through the infinite. Tonight, we're embarking on an extraordinary voyage to our nearest stellar neighbors, where something remarkable and deeply puzzling has just unfolded. Before we dive into this cosmic mystery, I'd love to know, where in the world are you watching from? And can you step outside right now and see the stars? There's something rather magical about discussing distant worlds while standing beneath the same sky that has guided humanity for millennia. If you find this celestial exploration soothing, enlightening, or simply a wonderful way to drift into dreams, I'd be ever so grateful if you gave this video a gentle like and perhaps subscribed. It helps this quiet corner of the cosmos reach other souls who might need a peaceful pause beneath the stars. Now, I do hope this isn't so captivating that it keeps you from your rest. But if it does, at least you'll have learned something extraordinary about our cosmic neighborhood before you settle in for the night. So find your most comfortable spot, slow your breathing, and let's begin our journey to Alpha Centauri, because sometimes the most profound discoveries come wrapped in the most beautiful mysteries. Just over 4 light years away from our little blue planet sits a stellar system that has captured human imagination for generations. Alpha Centauri, the third brightest star in our night sky, though visible only from the southern hemisphere, has always held a special place in our hearts and minds. It's our closest stellar neighbor, a cosmic next-door neighbor, if you will. And for decades, astronomers have wondered what secrets might be hiding in that distant system. The Alpha Centauri system is actually a cosmic dance of 3 stars. The 2 main performers, Alpha Centauri A and Alpha Centauri B, are remarkably similar to our own Sun. They waltz around each other in an elegant gravitational ballet, taking about 80 years to complete one full orbit. Meanwhile, a third, much smaller and dimmer red dwarf called Proxima Centauri lurks farther out like a shy wallflower at the cosmic dance. It's around this little red star that astronomers have already discovered 3 confirmed planets, including one that sits tantalizingly in what we call the habitable zone, that Goldilocks region where liquid water might exist. But the real prize, the discovery that would truly set hearts racing, would be finding planets around the Sun like stars Alpha Centauri A and B. These are the stars that most closely resemble our own solar system's architecture, and finding worlds there would tell us something profound about how common planetary systems like ours might be in the universe. For years, this quest has been like searching for fireflies next to searchlights. The brilliant light of these stars makes detecting any orbiting planets extraordinarily challenging. That's where NASA's James Webb Space Telescope enters our story. This remarkable instrument, launched just a few years ago, represents humanity's most sophisticated eye on the cosmos. Webb doesn't just look at distant galaxies billions of light years away, it can also peer with unprecedented precision at objects much closer to home. Using a technique called coronagraphy, Webb can create an artificial eclipse blocking out the overwhelming glare of a star to reveal the faint whisper of light from any planets that might be orbiting nearby. In August of 2024, Webb turned its golden eye toward Alpha Centauri A, and what it saw has left astronomers both thrilled and thoroughly puzzled. Using its mid-infrared instrument, Webb detected something extraordinary. A faint point of light separated from Alpha Centauri A by about twice the distance between Earth and our Sun. This object was more than 10,000 times dimmer than the star itself, a cosmic whisper against a stellar shout. The detection was technically magnificent. Webb's coronagraph had to not only block the light from Alpha Centauri A, but also account for the brightness of its companion star, Alpha Centauri B. The precision required was like trying to spot a candle flame while standing next to a lighthouse and having another lighthouse nearby. Yet Webb managed it, revealing this mysterious object that appeared to be exactly what astronomers had been hoping to find: a planet orbiting our nearest Sun-like star. Initial analysis suggested this could be a gas giant roughly the mass of Saturn, a world that would represent a tremendous discovery. If confirmed, It would be the closest exoplanet to Earth orbiting a sun-like star, and it would mark a new milestone in our ability to directly image worlds beyond our solar system. The scientific community began to buzz with excitement. Here was potential proof that planetary systems exist around stars very similar to our own sun, right in our cosmic backyard. But then something strange happened. When Webb looked back toward Alpha Centauri A in February of 2025, the mysterious object had vanished. The spot where it had clearly appeared in August showed nothing but empty space. When astronomers looked again in April 2025, the result was the same. No sign of the object that had been so clearly detected just months before. This disappearance might seem like bad news, like perhaps the original detection was an error or an instrument glitch. But in the world of astronomy, sometimes a disappearing planet is actually more convincing evidence of a planet than a planet that never disappears. You see, planets move. They orbit their stars in predictable paths, and depending on when you look, they might be visible, or they might be hidden behind their star, or simply too close to the stellar glare to detect. A team of researchers led by PhD student Aniket Sanghi at Caltech decided to treat this mystery like a cosmic detective story. They gathered all the evidence the August 2024 detection, the February and April 2025 non-detections, and even reached back to include a potential sighting from 2019 by the European Southern Observatory's Very Large Telescope. Then, they did what astronomers do best when faced with a puzzle. They ran computer simulations. These weren't just any simulations. The team modeled millions of possible orbits, testing every conceivable path this mysterious object could take around Alpha Centauri A. They had to account for the complex gravitational dance between the two main stars in the system, ensuring that any proposed orbit would be stable over long periods of time. A planet in an unstable orbit would eventually be flung out of the system entirely, hardly the kind of neighbor we'd expect to find after 4.5 billion years. The results of this cosmic detective work were fascinating. In about half of the simulated orbits, the planet would indeed disappear from Webb's view at exactly the times when the telescope failed to detect it. The modeling revealed a consistent picture, a world roughly the mass of Saturn, following an elongated elliptical orbit around Alpha Centauri A. This orbit would take the planet between 1 and 2 Earth-Sun distances from its star, completing one full revolution every 1.5 to 2.5 Earth years. Picture this cosmic dance for a moment. During part of its orbit, this potential world swings relatively close to Alpha Centauri A, where it would be heated and illuminated, making it easier for Webb to spot. But as it continues along its elliptical path, it moves farther away, becoming cooler and dimmer, until it essentially vanishes from Webb's sensitive but not infinite detection capabilities. It's like a cosmic game of peekaboo with a planet-sized player. The implications of this discovery, if confirmed, are staggering. This would represent the closest exoplanet to its star that has ever been directly imaged. Most planets detected through direct imaging are massive worlds orbiting at great distances from their stars, where the contrast between stellar glare and planetary light is more manageable. But this potential world at Alpha Centauri challenges our technical capabilities and pushes the boundaries of what's possible with current technology. Moreover, this planet would be remarkably similar in some ways to the giant planets in our own solar system. Its temperature and age would closely match those of Jupiter and Saturn, making it a perfect laboratory for understanding how gas giants form and evolve around sun-like stars. The fact that it exists in a binary star system where two stars orbit each other adds another layer of complexity and scientific interest. How does a planet form and survive in such a dynamic gravitational environment? The technical achievement represented by this potential detection cannot be overstated. Charles Beichmann from NASA's Jet Propulsion Laboratory described these as incredibly challenging observations, even for the world's most powerful space telescope. Webb was designed primarily to peer at the most distant galaxies in the universe, not to perform the delicate surgery required to tease out faint planetary light from nearby bright stars. The operations team at the Space Telescope Science Institute had to develop entirely new observing procedures just for this target. They created custom sequences that could account for the rapid motion of the Alpha Centauri system across the sky and the complex interplay of light from two bright stars. It was like performing microsurgery while riding a roller coaster, an extraordinary testament to human ingenuity and technological precision. This potential discovery also carries profound implications for the future of exoplanet science. If a gas giant exists at Alpha Centauri A, it raises tantalizing questions about what other worlds might be lurking in this system. Could there be smaller rocky planets closer to the star, perhaps even in the habitable zone where liquid water could exist? While a Saturn-mass gas giant wouldn't be habitable itself, it could potentially host moons, and those moons orbiting in the right location might just be able to support life. On August 7, 2025, NASA posted an article that the James Webb Space Telescope had found strong evidence of a giant planet orbiting a star in the stellar system closest to our own Sun. Webb used its mid-infrared instrument, MIRI, to provide the strongest evidence to date of a gas giant orbiting Alpha Centauri A. The results were accepted in 2 papers submitted to the astrophysical journal Letters. If this finding is confirmed, then the planet would be the closest to Earth that orbits in a habitable zone of a Sun-like star. Unfortunately, this planet is likely a gas giant, and scientists say it wouldn't support life as we know it. However, this planet may have moons that are also in the habitable zone, and as we learn more over time, maybe scientists will discover a moon that can sustain life, and it would sort of be like the movie Avatar. The story of planet hunting around Alpha Centauri has been filled with both hope and disappointment over the years. In 2012, astronomers announced the discovery of an Earth-mass planet around Alpha Centauri B, only to later retract the claim when follow-up observations suggested they had been fooled by stellar activity and noisy data. The scientific community learned hard lessons about the challenges of detecting planets around nearby stars and the importance of confirmation observations. But this new Webb detection feels different. The sophisticated modeling, the careful analysis of multiple observations, and the elegant explanation for why the planet appears and disappears all point towards something genuine. The researchers aren't claiming victory, yet they're seasoned astronomers who understand the importance of caution in a field where false positives have burned the community before. Instead, they're methodically building a case piece by careful piece. The beauty of this discovery lies not just in what was found, but in how it was found. The James Webb Space Telescope's mid-infrared instrument represents a revolution in our ability to peer through the cosmic glare. Its coronagraph technology essentially creates an artificial eclipse, allowing astronomers to block out starlight while preserving the faint glow of any nearby worlds. The instrument uses specialized masks and filters, working in concert, like a perfectly choreographed optical symphony to achieve contrast that seemed impossible just a few years ago. Think of it this way. Imagine trying to photograph a firefly that's hovering right next to a stadium's floodlight from several miles away. That's roughly the challenge Webb faced when looking for this planet. The fact that it succeeded even once is remarkable. The fact that the planet's disappearance and reappearance follow predictable patterns based on orbital mechanics makes the detection all the more compelling. The mid-infrared instrument operates in a part of the electromagnetic spectrum where planets glow with their own heat rather than just reflecting starlight. This thermal emission provides a crucial advantage because it means the planet doesn't have to be perfectly positioned to reflect light toward Earth. Instead, Webb can detect the warm glow of the world itself, the infrared signature of a distant atmosphere heated by its star and possibly by internal processes within the planet. This technique opens up entirely new possibilities for studying exoplanets. When astronomers eventually confirm this detection, they'll be able to analyze the planet's thermal spectrum breaking down the light into its component wavelengths like a cosmic fingerprint. This spectral analysis could reveal the composition of the planet's atmosphere, the presence of clouds or hazes, and perhaps even clues about how the world formed billions of years ago. The elliptical orbit, suggested by the modeling, adds another layer of intrigue to this cosmic story. Most planets in our solar system follow nearly circular paths around the Sun, but this potential world at Alpha Centauri A appears to take a more dramatic route, swooping closer to its star and then retreating to cooler distances. Such eccentric orbits often tell stories of cosmic violence, gravitational interactions, or close encounters that perturb the planet from a more circular path. In a binary star system like Alpha Centauri, the gravitational influences are complex and ever-changing. The two stars, Alpha Centauri A and B, orbit each other every 80 years or so, and during their cosmic dance, they create a constantly shifting gravitational landscape. Any planet trying to maintain a stable orbit must navigate this changing terrain like a ship sailing through tides that shift over decades rather than hours. The fact that a planet could survive and maintain a stable orbit in such an environment speaks to the remarkable resilience of planetary systems. It also suggests that planets might be far more common around binary stars than we previously imagined. Since roughly half of all stars in our galaxy are part of binary or multiple star systems, this could dramatically expand the number of potential homes for planets throughout the cosmos. The research team's approach to this mystery demonstrates the evolution of modern astronomy from individual observations to comprehensive data analysis. Rather than relying on a single detection, they've woven together multiple observations across several years, creating a temporal tapestry that reveals the hidden patterns of planetary motion. It's detective work on a cosmic scale using mathematics and physics as forensic tools. The computer simulations that helped solve this puzzle represent thousands of hours of computational work testing millions of possible scenarios. Each simulation had to account for the gravitational effects of both stars, the stability of various orbital configurations, and the observational constraints imposed by when and how Webb could detect the planet. The fact that roughly half of the viable orbits predict exactly the pattern of visibility and invisibility that was observed provides compelling support for the planetary interpretation. This methodical approach reflects hard-won wisdom from previous claims and retractions in exoplanet science. The astronomical community has learned to be simultaneously bold in its observations and cautious in its claims. Each potential discovery must run a gauntlet of verification, peer review, and independent confirmation before it can take its place in the catalogue of confirmed worlds. The timing of this discovery couldn't be more perfect. We're entering a golden age of exoplanet characterization, with Webb leading the charge and other next-generation telescopes preparing to join the hunt. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will carry even more sophisticated coronagraph technology, specifically designed for finding and studying planets around nearby stars. Roman's capabilities will complement Webb's discoveries beautifully. Where Webb excels in infrared observations, Roman will provide detailed visible light data, allowing astronomers to study the same planets across different wavelengths. This multi-wavelength approach will reveal details about planetary atmospheres, surface properties, and orbital characteristics that no single telescope could achieve alone. The potential for follow-up observations adds another dimension of excitement to this discovery. If the modeling is correct, Webb should have another excellent opportunity to spot this elusive world in August 2026, when the planet's orbit brings it back into the telescope's detection range. That future observation could provide the final confirmation needed to officially add this world to the growing catalogue of directly imaged exoplanets. But even if this particular detection remains tentative, the techniques and technologies demonstrated by this investigation will pave the way for countless future discoveries. Webb has shown that it can perform the delicate dance required to spot planets around nearby Sun like stars opening up our entire stellar neighborhood to detailed exploration. The Alpha Centauri system, with its 3 stars and growing collection of known and suspected planets, is becoming a Rosetta Stone for understanding planetary system architecture. Each new discovery there provides insights that can be applied to the thousands of other star systems scattered throughout our galaxy. It's our cosmic laboratory, a place where theories about planet formation and evolution can be tested against reality. As we drift deeper into this story of cosmic hide and seek, it's worth pondering what this discovery means for our place in the universe. If confirmed, this planet represents tangible proof that worlds can form and survive around stars very much like our own sun. It suggests that planetary systems aren't rare cosmic accidents, but perhaps common features of stellar evolution. The gentle dance of this potential world around Alpha Centauri A, its patient orbit through decades of cosmic seasons, reminds us that the universe operates on timescales far grander than our human experience. While we measure our lives in years, this distant planet, if it exists, has been following its elliptical path for billions of years, a cosmic metronome keeping time to rhythms we're only just beginning to appreciate. The story of this mysterious world near Alpha Centauri also illuminates the extraordinary evolution of our planet-hunting capabilities. Just a generation ago, the idea of directly photographing a planet orbiting another star seemed like pure science fiction. The first exoplanet around a sun-like star wasn't discovered until 1995, and that detection relied on the subtle gravitational wobble the planet caused in its star's motion. Now here we are, potentially watching worlds appear and disappear in real time as they dance around distant suns. This technological leap represents one of humanity's greatest achievements in precision engineering and scientific ingenuity. The James Webb Space Telescope's ability to block starlight while preserving planetary signals requires controlling light to extraordinary degrees. The coronagraph masks must be positioned with accuracy measured in fractions of a wavelength, while the telescope itself maintains pointing stability that would be like holding a laser pointer steady on a coin from hundreds of miles away. The mid-infrared instrument that made this detection possible operates in a realm of the electromagnetic spectrum that our eyes cannot see. At these infrared wavelengths, planets glow with thermal radiation, the warmth they've absorbed from their stars and generated through their own internal processes. It's a fundamentally different way of seeing the cosmos, one that reveals the heat signatures of distant worlds rather than their reflected light. This thermal detection method offers unique advantages for studying planetary atmospheres and compositions. When astronomers eventually obtain detailed spectra of this potential world, they'll be reading the infrared fingerprints of molecules in its atmosphere. Different gases absorb and emit light at specific wavelengths, creating patterns that astronomers can decode like a cosmic chemical analysis. The elliptical orbit proposed by the modeling adds layers of complexity to this world's story. Unlike the nearly circular paths followed by most planets in our solar system, this distant world appears to follow a more dramatic route. During its closest approach to Alpha Centauri A, it would experience intense stellar heating, while at its most distant point, it would cool significantly. These temperature variations could drive dynamic weather patterns and atmospheric changes across the planet's long seasonal cycles. The gravitational environment of the Alpha Centauri system creates a constantly shifting cosmic landscape. As Alpha Centauri A and B orbit each other, over their 80-year cycle, they alternately approach and separate, creating tidal forces that could influence any planets in the system. A world orbiting Alpha Centauri A must navigate these changing gravitational currents while maintaining its stability over cosmic time scales. The survival of planets in such complex gravitational environments speaks to the remarkable resilience of planetary systems. Computer simulations suggest that stable orbits are indeed possible around both Alpha Centauri A and B, but they require precise initial conditions and orbital parameters. The fact that this potential planet appears to have found such a stable configuration suggests that nature is quite skilled at creating and preserving these delicate cosmic arrangements. The research methodology employed by Sanghi and his colleagues represents a new paradigm in exoplanet confirmation. Rather than relying solely on detection or non-detection, they've created a comprehensive temporal model that explains the entire sequence of observations. This approach treats the planet's apparent disappearance not as a failure, but as additional data that constrains the possible orbital solutions. The team's Monte Carlo simulations tested millions of potential orbits, but only a subset proved both gravitationally stable and consistent with the observational record. This mathematical detective work demonstrates how modern astronomy combines observation with sophisticated modeling to extract insights from limited data. It's a testament to the power of computational astrophysics to reveal hidden patterns in cosmic behavior. The implications extend far beyond this single potential world. If gas giants can form and survive around Alpha Centauri A, it suggests that planet formation is a robust process that can occur even in complex stellar environments. This finding would support theories that planetary systems are common throughout the galaxy, not rare cosmic accidents, but natural outcomes of stellar evolution. The discovery timeline also reveals the patience required for cutting-edge astronomical research. The potential 2019 detection, the 2024 confirmation, and the 2025 non-detection span 6 years of careful observation and analysis. The proposed 2026 follow-up observation represents another milestone in this extended investigation. Such lengthy timescales are typical in astronomy, where cosmic motions unfold gradually and confirmation requires multiple independent observations. The technical challenges overcome by Webb's observations cannot be understated. The telescope had to precisely track the Alpha Centauri system as it moved across the sky, while simultaneously blocking starlight and detecting planetary signals. The custom observing sequences developed for this target pushed the instrument to its operational limits, demonstrating capabilities that its designers hoped for but couldn't guarantee until tested in space. The coronagraph technology at the heart of these observations represents decades of development and refinement. The concept of creating artificial eclipses to reveal hidden cosmic objects has evolved from simple disk masks to sophisticated multi-stage systems that can suppress starlight by factors of millions. Webb's coronagraphs achieve raw contrasts better than 1 part in 1,000 at small angular separations, improving to 1 part in 100,000 at larger separations. The 4-quadrant phase mask employed by Webb's mid-infrared instrument represents a particular triumph of optical engineering. This device manipulates the phase of light waves to create destructive interference that cancels out the stellar signal while preserving light from nearby sources. It's an elegant solution to the fundamental challenge of exoplanet imaging, the overwhelming brightness difference between stars and planets. Future observations will test this discovery in new ways and potentially reveal additional details about this mysterious world. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will observe Alpha Centauri with different instruments and techniques, providing independent confirmation and complementary data. Roman's visible light coronagraph will reveal different aspects of the planet's properties, including its size, reflectivity, and orbital characteristics. The broader scientific community awaits these confirmatory observations with keen interest. The potential discovery has already influenced observing strategies for other nearby star systems and informed the design of future exoplanet imaging missions. Success at Alpha Centauri would validate techniques that could be applied throughout our stellar neighborhood, opening dozens of nearby sun-like stars to detailed planetary surveys. The cultural impact of confirming a planet around Alpha Centauri A would resonate far beyond the scientific community. This star system has captured human imagination for centuries, featuring prominently in science fiction literature and representing humanity's first target for potential interstellar exploration. The reality of worlds orbiting our nearest stellar neighbors transforms these systems from abstract points of light into complex planetary systems with their own unique characteristics and histories. The potential for life on moons orbiting this gas giant adds another dimension of intrigue to the discovery. While the planet itself would likely be unsuitable for life as we know it, any large moons in stable orbits could potentially support liquid water and perhaps even biological processes. The Jupiter and Saturn systems in our own solar system host several moons with subsurface oceans, and the same could be true at Alpha Centauri. The detection methods pioneered for this investigation will influence exoplanet research for decades to come. The combination of direct imaging thermal spectroscopy and orbital modeling provides a comprehensive approach to studying distant worlds. As these techniques mature and spread to other targets, they'll reveal the diversity of planetary systems throughout our galactic neighborhood. The patient methodology demonstrated by this research also reflects the evolution of astronomical practice. The days of single decisive observations are giving way to extended campaigns that build understanding gradually through multiple measurements and analyses. This approach reduces the risk of false positives while building robust cases for genuine discoveries. The story of this potential planet also illustrates the international nature of modern astronomy. The research combines data from the James Webb Space Telescope, the European Southern Observatory's Very Large Telescope, and computational resources from institutions around the world. Science at this level requires global collaboration and shared expertise that transcends national boundaries. The economic investment represented by these observations is substantial. The James Webb Space Telescope cost over $10 billion to develop and launch, while each hour of observing time represents a significant allocation of precious resources. The fact that astronomers chose to dedicate multiple observation sessions to Alpha Centauri reflects the high scientific priority placed on characterizing nearby planetary systems. The educational impact of this discovery extends to inspiring the next generation of astronomers and engineers. Students around the world are following this investigation, learning about orbital mechanics, coronagraph design, and the statistical methods used to analyze complex data sets. These young scientists will carry forward the techniques and perspectives developed through this research. The philosophical implications of finding worlds around Alpha Centauri touch on fundamental questions about our place in the cosmos. Each new planetary system we discover expands our understanding of the possible ways matter can organize itself into complex structures. The diversity of exoplanets revealed over the past decades suggests that nature is remarkably creative in fashioning worlds with properties we never imagined. The timing of observations also reveals the complex choreography required for space-based astronomy. Webb's orbit around the second Lagrange point provides stable observing conditions, but also constrains when different targets are visible. The telescope must coordinate observations with Earth's orbital motion, the target's motion across the sky, and the operational schedules of other observing programs. The data processing required to extract planetary signals from stellar glare represents another technological frontier. The raw images from Webb contain far more photons from the star than from any planet, requiring sophisticated algorithms to separate signal from noise. These computational techniques continue to evolve with each new observation, improving our ability to detect ever fainter worlds. The potential discovery at Alpha Centauri also highlights the complementary nature of different detection methods. While transit surveys like those conducted by the Kepler and TESS missions excel at finding planets that cross in front of their stars, direct imaging reveals worlds in different orbital configurations. Together, these techniques provide a more complete census of planetary systems. The long-term vision for exoplanet science includes detailed atmospheric characterization of dozens of nearby worlds. The potential planet at Alpha Centauri would become a prime target for such studies, serving as a Rosetta Stone for understanding gas giant atmospheres around sun-like stars. The insights gained could then be applied to interpreting observations of more distant worlds discovered by future missions. As we contemplate this cosmic mystery unfolding in our nearest stellar neighborhood, we're reminded that the universe continues to surprise us. Each new observation reveals layers of complexity and beauty that challenge our assumptions and expand our perspectives. The potential world at Alpha Centauri represents not just a scientific discovery, but a testament to human curiosity and our relentless drive to understand our place among the stars. The gentle rhythm of this investigation, spanning years of observations and analysis, mirrors the patient timescales on which cosmic processes unfold. While we live our lives in moments and seasons, distant worlds follow orbital paths that span decades and centuries. Our growing ability to perceive and understand these grand cosmic rhythms represents one of humanity's greatest intellectual achievements. The journey to confirm this elusive world will require extraordinary patience and precision. Astronomers are essentially playing a cosmic waiting game where the next chapter unfolds according to celestial mechanics rather than human schedules. The proposed August 2026 observation window represents more than just another data point. It's a crucial test of our understanding of orbital dynamics and our ability to predict where distant worlds will be months or years in advance. The mathematical elegance underlying this prediction reveals something profound about the nature of scientific discovery. The same gravitational laws that govern the motion of our moon around Earth also dictate the dance of this potential planet around Alpha Centauri. Isaac Newton's insights from centuries ago continue to guide our expectations about when and where this distant world might next reveal itself to our most sophisticated instruments. Between now and that anticipated 2026 observation window, the astronomical community will refine their models and prepare new observing strategies. The James Webb Space Telescope will continue to push the boundaries of what's possible in direct imaging, while ground-based observatories contribute supporting measurements and theoretical insights. It's a coordinated effort that spans institutions and continents, all focused on understanding a single point of light in the cosmic darkness. The broader implications of this potential discovery ripple outward in fascinating ways. If confirmed, this world would join an exclusive club of directly imaged exoplanets, each one a laboratory for understanding planetary physics and atmospheric dynamics. These few dozen worlds detected through direct imaging represent the frontier of exoplanet science, where we can study individual planets in extraordinary detail rather than inferring their properties from indirect measurements. The thermal characteristics revealed by Webb's infrared observations offer tantalizing clues about this world's nature. Gas giants like Jupiter and Saturn generate their own internal heat through the slow gravitational compression that began during their formation billions of years ago. If this potential planet follows a similar pattern, it would glow warmly in infrared light, providing a thermal beacon that Webb can detect across the vast gulf of interstellar space. The atmospheric composition of such a world would tell stories spanning cosmic time. The mix of hydrogen, helium, and trace gases in a gas giant's atmosphere preserves chemical fingerprints from the planet's formation era. By analyzing the infrared spectrum of this potential world, astronomers could peer back billions of years to understand the conditions that existed when our stellar neighborhood was young and planetary systems were first taking shape. The elliptical orbit suggested by the modeling introduces seasonal variations that could create dynamic atmospheric phenomena. As the planet swings closer to Alpha Centauri A during its orbital summer, it would receive intense stellar heating, potentially driving powerful atmospheric currents and storm systems. During its orbital winter, at the farthest point from the star, the atmosphere would cool and contract, perhaps developing entirely different weather patterns. These temperature variations across the orbital cycle would create a natural laboratory for studying atmospheric dynamics under changing conditions. Unlike the relatively stable gas giants in our solar system, this potential world experiences dramatic climate variations that could reveal how planetary atmospheres respond to varying energy inputs. Such insights would prove invaluable for understanding atmospheric behavior on exoplanets throughout the galaxy. The detection methodology pioneered for this investigation represents a new chapter in humanity's quest to map our cosmic neighborhood. The combination of coronagraphy, orbital modeling, and multi-epoch observations creates a comprehensive approach that could be applied to dozens of nearby star systems. Each successful detection builds our confidence and refines our techniques for even more challenging observations. The Alpha Centauri system serves as a proving ground for technologies and methods that will eventually survey hundreds of nearby stars. Success here validates the fundamental approach of blocking starlight to reveal planetary companions, while the challenges encountered inform the design of future instruments and observing strategies. It's cosmic reconnaissance that prepares us for more ambitious surveys of stellar neighborhoods throughout our region of the galaxy. The international collaboration required for this investigation reflects the global nature of modern astronomical research. Data from American, European, and ground-based observatories combines with theoretical work from researchers around the world. The computational modeling that helped solve this cosmic puzzle drew upon expertise in orbital mechanics, gravitational dynamics, and statistical analysis from institutions spanning multiple continents. This collaborative approach also ensures that discoveries undergo rigorous peer review and verification before being accepted by the scientific community. The lessons learned from previous false alarms in exoplanet detection have created a culture of careful validation where extraordinary claims require extraordinary evidence and independent confirmation from multiple sources. The technological evolution that made this detection possible represents decades of incremental advances in optical engineering materials, science, and computational analysis. The James Webb Space Telescope's coronagraph capabilities build upon earlier ground-based instruments that first demonstrated the possibility of directly imaging exoplanets. Each generation of technology pushes the boundaries slightly further, enabling the detection of smaller, dimmer, and closer planets. The mid-infrared instrument that captured this potential planet operates in a wavelength range where Earth's atmosphere is largely opaque. Ground-based telescopes cannot make similar observations because water vapor and other atmospheric components absorb infrared radiation before it reaches terrestrial detectors. Only by placing Webb in the cold vacuum of space could astronomers access this crucial infrared window that reveals the thermal glow of distant worlds. The coronagraph masks and optical systems within MIRI represent marvels of precision engineering, manufactured to tolerances measured in fractions of a wavelength of light. These components must maintain their alignment and performance despite the thermal cycling temperature, gradients, and micrometeorite impacts that space telescopes endure throughout their operational lifetimes. The fact that these delicate instruments continue to perform at specification years after launch testifies to extraordinary engineering expertise. The data processing pipeline that extracts planetary signals from Webb's raw observations involves sophisticated algorithms developed specifically for high-contrast imaging. These computational techniques must distinguish genuine planetary light from instrumental artifacts, scattered starlight, and background objects that could masquerade as exoplanets. The software represents years of development and testing, refined through observations of known systems before being applied to discoveries like this potential world at Alpha Centauri. The statistical analysis that supports this detection employs Monte Carlo methods that test millions of possible scenarios to determine which orbital configurations remain consistent with the observational evidence. These simulations require substantial computational resources running for weeks on high-performance computing clusters to explore the vast parameter space of possible planetary orbits. The mathematical rigor underlying these calculations provides confidence in the conclusions while quantifying the uncertainties inherent in any astronomical measurement. The broader context of exoplanet demographics adds significance to this potential discovery. Current surveys suggest that gas giants are relatively common around Sun-like stars, with roughly 1 in 10 hosting Jupiter-sized worlds in orbits similar to those in our solar system. Finding such a planet at Alpha Centauri would confirm that our nearest stellar neighbors follow similar patterns of planetary formation and evolution. The binary nature of the Alpha Centauri system adds complexity to planetary formation scenarios that theoretical models are still working to understand. The gravitational perturbations from Alpha Centauri b would have influenced the formation and migration of any planets around Alpha Centauri a, creating conditions quite different from the relatively isolated environment where our solar system developed. Successful planet formation under such circumstances suggests that planetary systems are remarkably resilient and adaptable. The potential for additional worlds in the Alpha Centauri system remains an open question that future observations may help answer. If one gas giant exists around Alpha Centauri A, there could well be other planets in different orbital configurations, including smaller rocky worlds that current instruments cannot yet detect. The architecture of planetary systems often includes multiple worlds spanning a range of sizes and orbital distances. The habitable zone around Alpha Centauri A extends roughly from the distance of Venus to the distance of Mars in our solar system. While the potential gas giant appears to orbit outside this region, any rocky planets within the habitable zone could potentially support liquid water and perhaps even life. The detection of the gas giant could provide gravitational clues about the presence of smaller inner planets through subtle perturbations in its orbit. The moons of gas giants represent another frontier for astrobiological investigation. Jupiter's Europa and Saturn's Enceladus harbor subsurface oceans beneath their icy crusts, and similar moons around the potential Alpha Centauri planet could provide habitable environments, even if the planet itself lies outside the traditional habitable zone. Future instruments may eventually detect large moons around nearby exoplanets, opening entirely new realms for the search for life. The timeline for confirming this discovery extends well beyond the crucial 2026 observation. Even if Webb successfully detects the planet again, additional observations over multiple orbital periods would be needed to precisely determine its orbital parameters, atmospheric composition, and physical characteristics. The complete characterization of this world could span decades, as different instruments and techniques contribute pieces to the scientific puzzle. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will provide complementary observations using visible light coronagraphy. Roman's measurements will reveal different aspects of the planet's properties, including its size, albedo, and reflected light spectrum. The combination of Webb's infrared data with Roman's visible light observations will paint a comprehensive picture of this distant world. Ground-based, extremely large telescopes currently under construction will also contribute to the investigation. These 30-meter class instruments, equipped with advanced adaptive optics and coronagraph systems, will provide independent confirmation and additional spectroscopic capabilities. The convergence of multiple observational approaches increases confidence in discoveries, while revealing details that no single instrument could achieve alone. The educational impact of this investigation extends far beyond the immediate scientific results. Students around the world are learning about orbital mechanics, statistical analysis, and optical engineering through following this cosmic detective story. The methodical approach to hypothesis testing and model validation provides lessons in scientific reasoning that apply across disciplines. The public engagement opportunities created by this potential discovery help communicate the excitement and rigor of modern astronomical research. The story of a disappearing and reappearing planet captures imagination, while illustrating the patience and precision required for cutting-edge science. Such narratives help build public support for the substantial investments required for space-based observatories and long-term research programs. The philosophical implications of finding worlds around Alpha Centauri touch on humanity's relationship with the cosmos. Our nearest stellar neighbors transform from distant points of light into complex systems with their own planet's weather patterns and perhaps even moons with subsurface oceans. The universe becomes not just vast and ancient, but filled with worlds that follow their own rhythms and cycles. The potential for future interstellar exploration missions takes on new dimensions when we know what awaits at nearby stars. While current technology makes interstellar travel prohibitively challenging, the detailed characterization of exoplanets provides targets and motivation for future breakthrough propulsion concepts. The Alpha Centauri system could become humanity's first destination beyond our solar system. The economic implications of exoplanet discoveries influence funding priorities and technological development across multiple sectors. The techniques developed for astronomical coronagraphy find applications in medical imaging materials, characterization, and optical communications. The computational methods used for orbital analysis contribute to satellite tracking space, debris mitigation, and spacecraft navigation. The international cooperation required for major astronomical discoveries provides a model for addressing global challenges that transcend national boundaries. Climate change, pandemics, and resource management all benefit from the collaborative approaches and shared expertise that characterize modern astronomy. The scientific community's commitment to open data sharing and peer review offers lessons for other fields, grappling with complex global issues. The cultural impact of exoplanet discoveries influences art, literature, and popular understanding of our place in the universe. Science fiction authors draw inspiration from real discoveries, while educators use exoplanet research to engage students in physics, chemistry, and mathematics. The search for other worlds provides a compelling narrative that connects abstract scientific concepts to fundamental questions about existence and cosmic companionship. The technological spin-offs from exoplanet research continue to find applications in unexpected areas. The precision pointing systems developed for space telescopes improve satellite communications and Earth observation capabilities. The data analysis techniques used to extract planetary signals from noise enhance medical imaging, financial modeling, and pattern recognition across numerous industries. The long-term vision for exoplanet science includes detailed atmospheric characterization, biosignature detection, and perhaps even direct imaging of potentially habitable worlds. The techniques pioneered at Alpha Centauri will scale up to surveys of hundreds of nearby stars, creating a comprehensive census of planetary systems within our galactic neighborhood. Each new world discovered adds to our understanding of planetary formation, atmospheric evolution, and the potential for life beyond Earth. As we await the next chapter in this cosmic story unfolding at Alpha Centauri, we're reminded that the universe operates on timescales far grander than human experience. The patient orbit of this potential world has continued for billions of years, while our ability to detect and study it represents just the latest moment in an ongoing cosmic dance. Our growing capacity to perceive and understand these distant rhythms marks a profound expansion of human awareness and capability. The gentle persistence required for this investigation mirrors the broader qualities that define successful scientific inquiry. Progress comes not from single dramatic revelations, but from careful accumulation of evidence, patient analysis, and willingness to follow where the data leads. The potential planet at Alpha Centauri represents thousands of hours of observation modeling and analysis by researchers committed to understanding our cosmic neighborhood. The story continues to unfold with each new observation and analysis, adding details to our understanding of this mysterious world. Whether confirmed or ultimately refuted, this investigation demonstrates the power of modern astronomy to probe the deepest questions about planetary systems and our place among the stars. In the quiet spaces between observations, we wait and wonder what secrets the cosmos will reveal next. The methodical approach that has characterized this investigation reflects a fundamental shift in how we conduct astronomical research in the 21st century. Gone are the days when a single observation could establish or dismiss a planetary candidate. Today's discoveries emerge from careful orchestration of multiple instruments, observational campaigns, and theoretical frameworks all working together like instruments in a cosmic symphony. The patient rhythm of this research mirrors the very orbital mechanics it seeks to understand. Just as this potential world follows its leisurely dance around Alpha Centauri, taking years to complete each revolution, the scientific process unfolds according to its own measured cadence. Telescope scheduling, orbital visibility windows, and data analysis pipelines all contribute their own timing constraints to the investigation. The beauty of modern exoplanet research lies not just in what we discover, but in how these discoveries reshape our fundamental understanding of planetary formation and evolution. Each new world adds another data point to our growing statistical picture of how nature constructs planetary systems. The potential gas giant at Alpha Centauri would represent not just another exoplanet, but a crucial calibration point for our theories about planet formation in binary star environments. The sophisticated modeling that helps solve this mystery demonstrates how computational astrophysics has become an essential partner to observational astronomy. The millions of simulated orbits tested by Sanghi and his colleagues represent a kind of theoretical time travel, allowing researchers to explore how different planetary configurations would appear to our instruments across various observation epochs. These Monte Carlo simulations create virtual laboratories where astronomers can test hypotheses without waiting years for confirmatory observations. The mathematical models incorporate everything from basic Newtonian gravity to the complex three-body dynamics created by Alpha Centauri's binary nature. When half of these simulated scenarios predict exactly the observational pattern that was recorded, it provides compelling support for the planetary interpretation. The gravitational choreography of the Alpha Centauri system adds layers of complexity that make planet detection both more challenging and more scientifically valuable. The two primary stars orbit each other in an intricate dance that spans human lifetimes, creating a constantly shifting gravitational environment. Any planet orbiting one of these stars must navigate this changing landscape while maintaining orbital stability across cosmic timescales. The survival of planets in such dynamic environments speaks to the remarkable resilience of gravitational systems once they achieve stable configurations. Computer models suggest that while many initial planetary orbits would prove unstable over millions of years, those that do survive tend to be remarkably robust. The potential planet at Alpha Centauri appears to have found one of these stable havens where it can persist indefinitely. The thermal characteristics revealed by Webb's infrared observations provide tantalizing glimpses into the physical nature of this distant world. Gas giants like Jupiter and Saturn glow warmly in infrared light, partly from absorbed stellar energy and partly from their own internal heat, generated by gravitational compression during formation. This thermal signature creates a beacon that sensitive instruments can detect across interstellar distances. The wavelength range where Webb made this detection offers unique advantages for studying planetary atmospheres. Different molecules absorb and emit infrared radiation at characteristic wavelengths, creating spectral fingerprints that reveal atmospheric composition. Future detailed observations of this potential world could identify specific gases in its atmosphere, providing insights into its formation history and current physical state. The elliptical orbit suggested by the modeling introduces fascinating seasonal variations across this world's lengthy year during its closest approach to Alpha Centauri. The planet would experience intense stellar heating, potentially driving dramatic atmospheric dynamics. As it swings out to more distant reaches of its orbit, the reduced stellar energy input would create markedly different conditions. These orbital seasons would span Earth years rather than months, creating climate variations on timescales that dwarf anything we experience in our solar system. The atmospheric response to such extreme seasonal forcing could generate weather patterns and circulation systems unlike anything seen on the gas giants in our own neighborhood. Such a world would serve as a natural laboratory for understanding how planetary atmospheres respond to variable energy inputs. The precision required for these observations pushes current technology to its absolute limits. while pointing toward even more ambitious future capabilities. Webb's coronagraph must maintain optical alignment and stability while suppressing starlight by factors of tens of thousands. The achievement represents decades of advancement in materials science, precision manufacturing, and optical design. The custom observing procedures developed for the Alpha Centauri observations demonstrate the flexibility and sophistication of modern space-based telescopes. Unlike the rigid observing programs of earlier generations, Webb can adapt its pointing, tracking, and data collection strategies to match the unique requirements of each target. This adaptability proves crucial when studying nearby stars that move appreciably across the sky between observations. The international nature of this investigation reflects the global scope of contemporary astronomical research. Data from American space telescopes combines with observations from European ground-based facilities, while computational analysis draws upon expertise from institutions around the world. This collaborative approach ensures robust peer review while maximizing the scientific return from expensive observational resources. The verification process for exoplanet discoveries has evolved considerably following early false alarms that taught the community hard lessons about confirmation bias and the need for independent validation. Today's standards require multiple independent observations, consistent theoretical modeling, and careful consideration of alternative explanations before any detection can be considered confirmed. The statistical framework underlying this investigation employs sophisticated techniques for handling uncertainty and quantifying confidence levels. Rather than claiming definitive detection, the research team presents probability distributions that reflect the range of possible interpretations consistent with current data. This nuanced approach provides a more honest assessment of what we know and what remains uncertain. The educational value of following this investigation extends far beyond its immediate scientific results. Students learn about orbital mechanics through tracking the predicted positions of this elusive world. They explore statistical analysis through the Monte Carlo simulations that test millions of possible scenarios. They discover precision engineering through understanding how Webb's coronagraph achieves the contrast ratios needed for direct imaging. The public engagement opportunities created by this cosmic mystery help communicate both the excitement and the patience required for cutting-edge scientific research. The narrative of a disappearing and reappearing planet captures imagination while illustrating the methodical approach needed to extract reliable conclusions from limited observational data. The broader implications for exoplanet demographics could prove significant if this detection is confirmed. Gas giants appear to be relatively common around Sun-like stars, but finding one in the complex gravitational environment of a binary system would extend our understanding of where and how such worlds can form and survive. It suggests that planetary formation is a remarkably robust process, capable of succeeding even under challenging conditions. The potential for additional worlds in the Alpha Centauri system remains an intriguing possibility that future observations may explore. Planetary systems often contain multiple worlds, spanning different orbital distances and size ranges. If one gas giant exists around Alpha Centauri A, there could well be smaller rocky planets closer to the star or additional gas giants at greater distances. The techniques pioneered for this investigation will undoubtedly find application in surveys of other nearby stellar systems. Success at Alpha Centauri validates the fundamental approach of coronagraphic imaging, while the challenges encountered inform improvements for future instruments and observing strategies. Each nearby star system surveyed adds to our growing census of exoplanetary diversity. The Nancy Grace Roman Space Telescope will provide crucial complementary observations when it launches in the coming years. Roman's visible light coronagraph will reveal different aspects of planetary properties, including size, reflectivity, and scattered light spectra. The combination of Webb's thermal infrared data with Roman's reflected light measurements will create a comprehensive portrait of any confirmed worlds. The ground-based, extremely large telescopes currently under construction will also contribute to future Alpha Centauri observations. These 30-meter class instruments equipped with advanced adaptive optics will provide independent confirmation while offering spectroscopic capabilities that complement space-based measurements. The convergence of multiple observational approaches strengthens confidence in discoveries while revealing details beyond the reach of any single facility. The timeline for complete characterization of this potential world extends well into the next decade and beyond. Even successful confirmation in 2026 would represent just one milestone in a comprehensive investigation spanning multiple orbital periods. Understanding this world's atmospheric composition, orbital evolution, and physical characteristics will require sustained observation campaigns using multiple instruments and techniques. The patient methodology demonstrated throughout this investigation exemplifies the evolution of astronomical practice in the era of precision measurements and sophisticated data analysis. The days of single decisive observations have given way to extended campaigns that build understanding incrementally through careful accumulation of evidence and rigorous statistical analysis. The cosmic perspective offered by this potential discovery reminds us that we inhabit a universe filled with worlds following their own rhythms and cycles. Each planetary system represents a unique experiment in gravitational dynamics, atmospheric evolution, and perhaps even biological development. The diversity revealed by exoplanet surveys suggests that nature is remarkably creative in fashioning worlds with properties we never imagined. The technological achievements that made this detection possible represent humanity's growing capability to perceive and understand cosmic processes operating on scales far beyond direct human experience. We can now detect the thermal glow of distant worlds, measure their orbital motions, and begin to characterize their atmospheric properties. These capabilities would have seemed like pure fantasy just a generation ago. The philosophical implications touch on the fundamental questions about our place in the cosmic order. Finding worlds around our nearest stellar neighbors transforms abstract points of light into complex systems with their own geological, atmospheric, and perhaps even biological histories. The universe becomes not just vast and ancient, but populated with countless worlds, each following its own evolutionary path. The economic investments required for such discoveries influence technological development across multiple sectors while generating innovations that find unexpected applications in medicine, communications, and materials science. The precision engineering developed for astronomical coronagraphy contributes to advances in optical systems manufacturing processes and quality control methods throughout industry. The cultural impact extends through literature, art, and popular understanding of humanity's cosmic context. Science fiction authors draw inspiration from real discoveries, while educators use exoplanet research to engage students in fundamental concepts of physics, chemistry, and mathematics. The search for other worlds provides compelling narratives that connect abstract scientific principles to questions of existence and cosmic companionship. The long-term vision for exoplanet science includes detailed atmospheric analysis, biosignature detection, and perhaps even direct imaging of potentially habitable worlds. The methods developed at Alpha Centauri will scale to comprehensive surveys of hundreds of nearby stars, creating a detailed map of planetary systems throughout our galactic neighborhood. As we drift toward the conclusion of this cosmic tale, we find ourselves poised between confirmation and mystery, between what we think we've discovered and what future observations will ultimately reveal. The potential world at Alpha Centauri exists for now in that fascinating liminal space where scientific discovery often dwells suspended between hypothesis and verified fact. The gentle cadence of this investigation mirrors the patient rhythms that govern all meaningful scientific progress. Understanding emerges not from sudden revelations, but from careful accumulation of evidence, thoughtful analysis, and willingness to follow wherever the data might lead. Whether this particular detection proves genuine or eventually fades into the catalogue of interesting but unconfirmed candidates, it has already advanced our capabilities and deepened our appreciation for the challenges of detecting distant worlds. The story that began with a mysterious point of light appearing in Webb's infrared images has evolved into a sophisticated investigation employing cutting-edge technology, theoretical modeling, and international collaboration. It demonstrates both the power of modern astronomy to probe fundamental questions about planetary systems and the patience required to extract reliable conclusions from the vast cosmos that surrounds us. In the quiet moments between observations, as astronomers await the next opportunity to glimpse this elusive world, we're reminded that the universe operates according to its own schedule. The cosmic clockwork that governs planetary orbits, stellar evolution, and galactic rotation unfolds across timescales that dwarf human experience. Yet our growing ability to perceive and understand these grand rhythms represents one of our species' most profound achievements. The gentle mystery of this potential planet near Alpha Centauri continues to unfold with each analysis, each model, each carefully planned future observation adding new dimensions to our understanding. Whether confirmed or ultimately explained by alternative mechanisms, this investigation has already enriched our knowledge of what's possible in the cosmos and expanded our technical capabilities for exploring the worlds that await discovery among the stars. And so we find ourselves at this moment suspended between worlds, between what we've observed and what we hope to confirm, between the patient methodology of science and the profound questions that drive human curiosity about our place in the infinite expanse that surrounds our small blue home. The story continues, and in its continuation lies both the beauty and the promise of our endless quest to understand the cosmos and our place within it. The beauty of this cosmic investigation lies not just in the potential discovery itself, but in what it reveals about humanity's evolving relationship with the universe around us. We've reached a remarkable threshold where we can peer across the vast gulf of interstellar space and detect the gentle thermal whisper of worlds orbiting distant suns. The faint infrared glow captured by Webb represents photons that began their journey at Alpha Centauri over 4 years ago, carrying with them the story of a world that may have been dancing around its star since before life emerged on Earth. This potential planet, if confirmed, would join an exclusive collection of directly imaged worlds scattered throughout our cosmic neighborhood. Each of these distant companions tells its own story of formation, evolution, and survival in the complex gravitational environments that surround other stars. They represent laboratories where we can test our theories about how planets form, how atmospheres evolve, and how entire systems maintain their delicate gravitational choreography across billions of years. The methodical approach that has guided this investigation reflects a profound maturation in how we conduct astronomical research. The careful orchestration of observations, the sophisticated modeling of orbital possibilities, and the patient accumulation of evidence across multiple years all demonstrate our growing sophistication in extracting reliable insights from the cosmos. We've learned to listen carefully to what the universe whispers, rather than rushing to conclusions based on single tantalizing glimpses. The technological marvel that makes such discoveries possible continues to astound even those who designed and built these remarkable instruments. The James Webb Space Telescope operates in the cold depths of space, precisely maintaining optical alignment while tracking moving targets and suppressing overwhelming stellar glare to reveal the faintest planetary signals. It's a testament to human ingenuity that such delicate measurements are possible across the immense distances that separate us from our stellar neighbours. The international collaboration required for this investigation embodies the best traditions of scientific inquiry, where national boundaries dissolve in the face of shared curiosity about the cosmos. Researchers from different continents contribute their expertise in orbital mechanics, data analysis, and theoretical modelling, creating a collective intelligence that exceeds what any single institution could achieve alone. It's a beautiful example of how science transcends political divisions to pursue understanding that belongs to all humanity. The patient timeline that governs this investigation mirrors the vast scales on which cosmic processes unfold. While we measure our lives in decades, planetary orbits span years or centuries, and the formation of entire systems occurs across millions of millennia. Our growing ability to perceive and understand these grand rhythms represents a profound expansion of human consciousness, allowing us to think and plan across timescales that our ancestors could never have imagined. The potential confirmation awaiting us in the summer of 2026 carries with it the quiet excitement that defines the best of scientific discovery. Whether Webb detects this elusive world again or finds only empty space, the investigation will have advanced our capabilities and deepened our understanding of what's possible in the realm of planetary detection. Science progresses through such patient accumulation of evidence, building understanding one careful observation at a time. The broader implications stretch far beyond this single potential world to encompass our growing census of planetary diversity throughout the galaxy. Each new discovery adds another data point to our understanding of how nature constructs these cosmic systems, revealing patterns and possibilities that challenge our assumptions and expand our imagination. The universe appears to be remarkably creative in fashioning worlds with properties that span an extraordinary range of possibilities. As we drift toward the conclusion of tonight's gentle journey through this cosmic mystery, we find ourselves enriched by the wonder of discovery and the patient methods that make such revelations possible. The potential world near Alpha Centauri, whether confirmed or not, has already expanded our horizons and reminded us that the universe continues to hold secrets waiting to be unveiled by those patient enough to listen carefully to its subtle whispers. So, as you settle into your evening rest, perhaps step outside for a moment if the sky is clear and the stars are visible. Look toward the southern horizon if you can, where Alpha Centauri hangs in the cosmic darkness, and remember that somewhere in that distant system, a world may be following its ancient orbital path, carrying with it stories of cosmic evolution that span billions of years. We live in an age of wonders, where such distant mysteries can be probed and understood through the marriage of human curiosity and technological precision. The gentle rhythm of discovery continues, patient as starlight, persistent as gravity, beautiful as the cosmic dance that connects all worlds beneath the infinite sky. Sleep well, fellow travelers, knowing that tomorrow the universe will still be there, waiting with its endless mysteries and quiet revelations, ready to share its secrets with those who take the time to look up and wonder.